The Economist.
The technology world was roiling last week as it came to terms with the launch of a new artificial intelligence model called R1 from a Chinese startup, DeepSeek.
Chinese AI model is taking the world by storm and causing chaos on the financial markets.
As the world continues to laud the latest AI breakthrough, DeepSeek,
shockwaves through the tech industry. It's a new chatbot known as DeepSeek. The company.
Arguably, R1 was the biggest public moment for artificial intelligence since the launch of OpenAI's ChatGPT in November 2022. As Alex Hearn, The Economist's AI writer, explained on our sister podcast, Money Talks, last week.
DeepSeek R1 is one of a class of AIs called reasoning models. They take a question, they break it down, think it through step by step, try different approaches to solving the riddle until they come up with a final answer.
R1 is about as good as some of the best large language models made by Google, Meta and OpenAI. It was a lot cheaper to make. It's also open source. That means its weights and methods are published and available for anyone to download, replicate, and reuse. Among its many achievements, R1 is a powerful vindication for the open source movement. And no one embodies that drive more than Yann LeCun, chief AI scientist at Meta and a professor at New York University. He's also one of the godfathers of modern machine learning.
The reason why we've seen such an incredible acceleration of progress in AI over the last 12 years or so is because of openness, open research, open source. And until fairly recently, most of the big players were kind of practicing open research.
Yann LeCun has been working on artificial neural networks for decades. At Meta, he leads the team behind Llama, the company's family of open source models. This week, along with 6 other pioneers of machine learning, he was awarded the Queen Elizabeth Prize for Engineering here in Britain. Before he picked up his award, he came into the studio to tell us why open research is the fastest way to advance the science of AI, why he thinks large language models can't be the whole story if we want capable machines, and how AI models need a much better understanding of the world around them if they're to reach their full potential.
How is it that we have systems that can pass the bar exam and, compute integrals and solve math problems, but we still don't have a domestic robot that can clear up the dinner table and fill up the dishwasher, a task that any 10-year-old can do the first time they try? But ultimately, I think we're going to have to change the paradigm.
I'm Alok Jha, and this is Babbage from The Economist. Today, Yann LeCun on where AI goes next. Yann LeCun, thank you very much for joining me.
Thanks for having me on.
Yann, can I ask you about the most recent news when it comes to AI? Everyone's obsessed with the DeepSeek R1 model, and you've probably had a lot of people asking you, but I'd like to know, what was your initial reaction when you saw that model?
I mean, I welcome the innovation, and I welcome the fact that it came with a paper that explained everything about the techniques that they used, and also came with open source code. And so the result of this is that the entire community is going to profit from the innovation they came up with, which is, interesting. It's not like revolutionary, but it's well done.
What did you think of the model itself? You said it's not revolutionary, but it's still pretty well capable a model. And I guess people in the West who maybe weren't looking so closely were a bit surprised. So what was your sort of initial reaction to the capabilities of the model given what they've done?
So one thing that a lot of people in the community are working on is trying to sort of bolt reasoning abilities on top of large language models. Because large language models by themselves are basically incapable of reasoning. So the question is, how do you get them to do some level of reasoning, but not changing the basic paradigm? And they did a pretty good job at this. I mean, they showed that if you put a little bit of reasoning done right, you can get to the same level of performance as systems that would otherwise be much bigger and would have to basically learn by rote instead of coming up with new solutions, basically. But ultimately, I think this is not the way future systems are going to reason and plan. They're going to do that differently. So it's a good advance in the current paradigm. Eventually, we're going to have to change the paradigm.
Yeah, we'll come back to how you think things are going to advance, because that's going to be a really interesting part of the conversation. But did the emergence of that model surprise you in any way, though? Because, as you say, the biggest labs, yours included, OpenAI, others, are just starting to come out with these reasoning models to improve large language models. And the fact that DeepSeek came out with not only one, but two models very quickly. Was it a surprise, or do you think that because it's open source, because the code is available for the basic stuff, that this was inevitable?
It was inevitable in a way. I mean, it was not a huge surprise in the sense that DeepSeek had been working on the problem for a number of years and had published...
You'd seen their progress, had you?
Yeah, that's right. I mean, this is DeepSeek V3 and R1, R1.0, and they had DeepSeek V1, V2.
They had the
that,
V1
right?
and V2, of course, yeah.
So if you paid attention, you knew there was some good things were happening there. I think one big lesson from this event is that if you have a small group of talented people with a long leash and a long horizon, and you let them work, they'll come with probably more innovative ideas than if you have a large group of people that is directed towards innovating on a timeline. That's very difficult. You're not going to get breakthroughs if you tell people you're going to have the new model in the next 3 months or 6 months. You get innovation when you let people with
Give me a breakthrough in 1 month and another one a month after that. Doesn't work.
It's not happening.
I mean, I suppose the DeepSeek announcement is good for consumers, it sounds like, because, if you make models that are capable much cheaper, that's probably a good thing for everyone, and competition is always good. But I guess also what it does is show that open source software is something that will benefit people. And this is something that you are probably the best and most vocal advocate for. Why is open source so important to you as a person? What does it mean in the context of AI as well?
So if your purpose is to make fast progress in science and technology, what you need to do is involve the largest possible number of smart people and have them exchange information as quickly as possible so that those ideas kind of collide with each other and progress comes out of it. And it's accelerated if, first of all, people publish their work quickly without going through the delays of the traditional peer review process. So one thing I've been advocating for over 15 years, 20 years, is pre-publishing on preprint repositories like Archive, and then exchanging open source code, which basically puts the tools in the hands of everyone. So the reason why we've seen such an incredible acceleration of progress in AI over the last 12 years or so is because of openness, open research, open source. And until fairly recently, most of the big players outside of academia, including industry, were kind of practicing open research. But then because of a misplaced attempt at, and perhaps a bit of a superiority complex from some players, some outfits started climbing up. So OpenAI is closed. Anthropic is very secretive. Google, to some extent, has climbed up a little bit. And they're not revealing, to a large extent, what the techniques are. Now, I think it's going to hurt them more than it's going to hurt the world of open source. Meta has been on the side of open sourcing its platform software with Llama, which basically jump-started the whole industry. Because in the end, there's more people contributing. You have systems that work better, have higher performance, are more secure, and it's just going to progress faster.
Yeah, I mean, all of that makes sense. I guess what you've described is a very typical scientific process. In every other field,
Absolutely.
When you publish in a journal, you establish your primacy there. That's your idea. You've published it, you've peer-reviewed it, or put it on the archive, for example. But it's out there, and then other people can iterate on it, and that's typical science. But I guess that is typical science when it's just science and the money's coming in from grant funders or philanthropies or whatever. But of course, the difference with computer science now is that it's part of possibly the biggest industry and the most investment in the world. And so I guess there is a tension there. How do you manage that tension? Because at the same time as publishing all the research that you want to publish and the new models and everything, which we'll talk about, I'm guessing that someone in your managerial chain wants to actually monetize some of this stuff quickly.
Yeah, but the monetization is not hurt at all by open sourcing the platforms. In fact, it's really in the DNA of Meta as a company. Open sourcing software platforms is something that Meta has been doing since day one, not just in AI, but in all kinds of different domains. So it doesn't hurt the business whose revenue come from advertising and things of that type. Now, the products that you build on top of those platforms are not open source, but the platforms themselves are. And when you think about it, historically, in, let's say, the internet, those kind of open source platforms always end up winning. So back in the late 90s, for example, a bunch of companies were competing to provide the infrastructure of the internet, hardware and software, mostly software. So companies like Sun Microsystems, Hewlett-Packard, Microsoft. In the end, they all lost. What won was Linux. The entire internet runs on Linux. And not just the servers, also the routers. Also, when you access the internet through your phone, it talks to a cell phone tower. That runs on open source stack. So whenever there is a platform, the market pushes for those platforms to become open source because it's just more efficient.
Yeah. What are the limits to that when it comes to what can be open source and what can't? You've talked about the platform being open source. Perhaps the products are not. But in terms of artificial intelligence then, is the training data open source? Is the algorithm open source? What does it mean, just so that people understand?
Okay, so it's actually a very difficult definition for what open source means in this context, right? Yeah. So the first thing you can open is the code that runs the model after it's trained. Technically, it's not open source because most of those things come with restrictions about what you can do with them for legal reasons. They're not because, companies like Meta want to put restrictions. It's just because the legal landscape is such that you have to put those.
So you can't use it to build a bomb or something like that?
Something like that, yeah. or do illegal things, blah, blah, blah. Yeah. It's for liability protection. Yeah. Then you have the weight file, the parameter file, basically the result of training the system. A neural net has a set of numbers basically that defines its function. And you can provide this for free or not. So in Llama, it is free. In ChatGPT, it's not.
Just for comparison, how does it compare with the DeepSeek open source? Because they provide the weights as well. And I believe they also provide the underlying code.
So they provide the code for running the model. They provide the weights. Okay, and then you get into the code that is used for training the model. And most of those are not open source. There are a few that are open source, but most commercial companies don't actually give their training code.
This is the code that someone's written before the model itself was trained. These are the algorithms underneath it all.
That's
basically.
Right.
Yeah. And so there are different levels of this, right? So how do you make sure with a model like Llama, which you provide freely, how do you make sure that it isn't used in ways that you would perhaps find malicious or illegal or anything like that? I mean, is that something that you think about, or do you think at some point people are going to do what they do with it, and so it's not your responsibility?
Well, there's several levels. So first of all, Llama goes through a lot of fine-tuning and what we call red teaming, which is attempting to try to kind of get
make it do something bad,
right? Yeah. And it's kind of, fine-tuned so that it doesn't do that. Now, truthfully though, once you put a model out there, people can try to kind of jailbreak it, basically to kind of give it a prompt that will...
Yeah, this is all over the internet, isn't it? Yeah, you're getting all sorts of models to do sort of crazy things.
Right. Or, of course, if you are a little more sophisticated, you can fine-tune it to sort of unlearn those limitations. But in the end, the kind of stuff you can do with a large language model is not that dangerous or risky or whatever.
Not yet.
And people will do bad things with, all kinds of things, right? I mean, you can, you can bash people on the head with a stick, but we don't ban sticks just for that reason. There was a big fear a few years ago that perhaps those things would be used to kind of flood the internet with disinformation. Turns out that's just not happening. You don't need AI systems to flood the internet with disinformation.
Humans can do it very well. Yeah.
Sadly, organizations like QAnon is, two guys, and they don't need AI. And we've not seen this, talking to my colleagues at Meta who are in charge of what we call integrity. They've not seen a flood of disinformation, like AI-generated content, really.
Let's talk about the current state of the technology. I'd love to know what you think about the sort of language models that are out there, the really big ones from your labs and others. We call them intelligent. Are they really? How intelligent are they? And how do you even define it in this context?
Okay, so the first thing to realize is that intelligence is not a linear thing where you are more intelligent or less intelligent. It's very multidimensional. You can buy a gadget for 20 pounds that will beat you at chess. You beat me at chess, certainly. It doesn't mean that system is more intelligent than you. It's more intelligent for chess. And what we see is an increasing number of tasks for which machines are more intelligent than us. So what LLMs are really good at doing is manipulating language and producing language. And as it turns out, producing and manipulating language is simple because, we think of language as being sort of the epitome of human intelligence. It turns out to be simple.
Well, if you've got lots of GPUs, then yes.
A reasonable amount. But it's simple because it's discrete. What we're not able to do with AI systems today is dealing with the real world, understanding the real world, not even as well as a cat or even a rat. So in some directions, Our AI systems are as smart as a lawyer passing the bar exam. You know, they can answer all the questions or solve some math problems if they fall into some standard template. But on the other hand, they can't do what a cat can do. They can't do what a 10-year-old can learn in one shot. They can't learn in 20 hours how to drive a car, which, you know, any 17-year-old can do. So, you know, we have huge blind spots in the ability of AI systems to be able to do. And the problem is that those blind spots are not going to be filled by just training bigger LLMs on more text. It's going to require new architectures, a new paradigm of AI system. It's still going to be deep learning, it's still going to be neural nets, it's still going to require lots of GPUs, but new architectures that are capable of understanding the physical world, capable of having persistent memory, capable of reasoning, and capable of planning. And that's the big challenge for the next 5 to 10 years.
Well, you mentioned reasoning, so let's talk about that one. Large language models, of course, have come into the public consciousness in the last few years, and every company seems to be getting bigger and bigger computing clusters to train bigger versions of these models to see what can come from that. And in recent months, we've had these so-called reasoning models, which, as far as I understand it, are iterations of the large language models which ask themselves lots of questions before giving you a final answer. I mean,
basically,
you have a better definition, but maybe you can explain it to me then.
Okay, so there are two reasoning techniques that everybody has been working on for a few years. One of them is called chain of thought. So basically you coerce the system into actually kind of not producing a simple answer, but like producing a sequence of thought that led to the answer. Okay, and you can train it to do that. And you can train it by giving it the process of reasoning or by just training it to produce the right answer and then have it figure out what the proper process is, which is one of the things that DeepSeek R10 does. Or, an alternative to this, you can have the system produce lots and lots of sequences of tokens or words, and then have a separate system basically figure out which one among all of those is the best one, and then produce that one. Both of those things require more computation at runtime. So people have called that test time computation. And that makes running those systems much more expensive, which is why you have to pay a fortune to run the latest model of ChatGPT that is capable of this kind of reasoning. I don't think ultimately that's the answer. My money and what I work on is this other paradigm, which, you know, will take a longer time to develop. And so for people who are interested in like producing the next generation of product, you can afford to kind of wait 3 to 5 years. You have to really bring the innovation as fast as you can. But we're really kind of working for the longer term. So those are systems that basically will learn to construct some sort of mental model of the world that would allow them to reason. Like if I tell you, imagine a cube floating in front of you, and imagine you're rotating this cube by 90 degrees along a vertical axis. You can sort of visualize this thing and sort of do this action and then anticipate what the result of this is going to be and what the cube is going to look like after you rotate it. You have a mental model, which is geometrical, has nothing to do with language. Okay, a lot of animals are capable of doing this. When you see a cat sort of planning to jump over a bunch of furniture, you know, they have this kind of model in
This is a sort of inherent feeling about the physical world around you, basically.
Common sense, right? And so if you have this kind of mental model, you can imagine what the outcome of a sequence of action you might take will be, and you can predict whether this sequence of action will satisfy an objective you set for yourself or a goal. And therefore, you can plan a sequence of action that will satisfy this goal using your inner mental model. And animals are capable of this. So we can say confidently that it has nothing to do with symbols or languages, right? A cat can do this. A rat can do that. That's system 2. So this is the kind of stuff that we're working on. But again, you know, it's difficult.
Yeah, just to define the system 1, system 2, this comes from the Daniel Kahneman idea that system 1 in a human being is the immediate reaction to something, like the fear or some emotion like that. System 2 is when you have an interaction with something that you think about, and you'll get a better answer as a result. And these are metaphors, really, for the intelligence in machines. They're not exactly the same thing.
Well, think any task that, you know, a human accomplishes for the first time, usually you devote your entire attention to it, like you learn to drive or something.
You really have to think, You
have to think about what you're going to do, and you imagine all kinds of catastrophe scenarios and everything. And after, 20, 30 hours of having driven, you can do this subconsciously and you can sort of talk to someone. So you went from like using your entire mental abilities to basically turning it into a subconscious task. So that's going from system 2 to system 1.
Well, let's talk about your way of doing this then. We've talked about chain of thought reasoning, which is the current sort of vogue in the models. I'm assuming also with the next iteration of Llama, you might have chain of thought thinking going on, because that's possible now with the amounts of compute that's happening. But I'm interested in the planning, the hierarchical thinking that you mentioned as well. And this is a new architecture for neural nets that you've promoted for a long time. Just talk to us about the joint embedding predictive architecture, JEPA. So how does what you've described fit into that architecture? And how does that differ from the kind of architectures that people are using today with LLMs?
Okay, so the way an AI system should work is that you give it a clear objective, accomplish this task, and then what it's trying to do is figure out a sequence of actions that will accomplish this task, right? It could be a physical task, or it could be an intellectual task, or it could be just answering a question. And so that process involves searching through the space of possible answers or possible outputs for one that actually will accomplish the task. And to be able to figure out if a sequence of action will accomplish the task, you need a mental model of the world. You need to basically feed that sequence of action to your mental model and then imagine what's going to happen when you accomplish those actions and verify that the goal is being accomplished. So that's planning and reasoning. And so when you use a LLM, you're not giving it a goal. You're just kind of writing a prompt and you just cross your fingers that the training of the system will have it sort of complete that prompt with the answer that you seek. But there's no explicit goal that an LLM accomplishes.
It doesn't understand anything.
Well, I mean, it has some level of understanding, but it doesn't have like an explicit goal to fulfill. And that makes it difficult to control. So the way an LLM is trained is that you take a piece of text and then you train a large neural net to predict the word that comes after that piece of text. It turns out that's a relatively simple task. The reason it's simple is because language is discrete. There's only a finite number of words, possible words in a dictionary. And so predicting the next word, you can never predict exactly which word is going to come after a particular sequence of words, but you can produce a probability distribution of all possible words in the dictionary. And that turns out to be relatively simple. Now, the idea that you should use this process, which by the way is called self-supervised learning, to train a system to understand the physical world is very old. People have been working on this for decades. I've been working on this for the better part of the last 20 years. And so the idea is similar. Take a video and then train a system to predict what's going to happen next in the video. And if it's able to do this, then it will have understood something about the underlying nature of the physical world, that the world is composed of, objects that can move and things like that.
Gravity, etc.
Gravity, all that stuff. And this is the kind of stuff that young animals and young humans learn in the first few months of life. It takes babies about 9 months to figure out what gravity is and the fact that every object that is not supported needs to fall, with a few exceptions. So how do we reproduce this kind of learning in machines? And why is it the case that those techniques work for text and they don't work for the real world? They don't work for the real world because the real world is much, much more complicated than language. We cannot predict what's going to happen next in the physical world. We cannot even mathematically represent a probability distribution about,
There's too many things to think.
There's just too many things that can happen, and it's mathematically intractable. It's a problem that physicists have encountered for decades, like since the 1940s. And they've tried to devise methods to get around this, but it's completely intractable. And so the idea of JEPA is that you don't train a system to predict all the details of what happens in the video. You train a system to learn an abstract representation of the real world, of the video, in such a way that within this abstract representation space, you can make that prediction. So if I take a pen and I put it on the table with my finger on it, and I remove my finger, you know that the pen is going to fall. You can't predict in which direction. But at some abstract level, you can tell the pen is going to fall. I just can't tell you in which direction. Okay, so if I train the system to predict the pixels of what the pen is going to look like after it falls, I can't, because I can't know the direction. But at an abstract level, I can tell you it's going to fall. This process of abstraction, finding abstract representations, is really fundamental to intelligence.
Do you have to give it the laws of physics? Do you have to give it information, or are you expecting the network to work all these abstractions out by itself? And how does it know that something is correct? So
we're not giving it much. No, we're not giving it any physical law or anything like this. We just expect the system to learn it from data. The way an animal or, an infant would do it, by basically observing the regularities in the real world. In the first 3 or 4 months of life, human babies basically cannot really act in the world. Most of what they learn is by observation. And they learn a great deal, a huge amount of background information that we don't realize is really difficult because we take it for granted. But
I guess they know that things fall, but they don't know the laws of physics. So yeah.
Well, they don't know that things fall until later, actually. It takes several months, 6 months, 8 months, and then put a 8-month-old on a high chair with a bunch of toys. What the 8-month-old will do is take the toys and throw them on the floor to verify that gravity actually works on those objects. So at some point, babies, make experiments in the world. But no, we're not giving this kind of information system. We're just training them on video. And what we've been surprised in seeing, we just finished a paper on this, is the fact that if we train a video prediction system on very short video, just 16 frames or something like this, to basically complete a video, not necessarily in time, but also in space. So like blocking a piece of the video and training the system to predict the representation of a full video. What we notice is that those systems basically have acquired some level of common sense. They can tell if you show them a video that's impossible, where you have a ball rolling and then it disappears, or it turns into a cube. You can measure the prediction error in the system and it shoots up because the system says, like, that's impossible. I've never seen this before. Or you have a ball rolling behind a screen, and then the screen comes down and the ball has disappeared. Same thing, the prediction error will shoot up. And so those systems have basically figured out what can happen and what cannot happen to some level. And we're really hoping that the next generation of those systems will have some level of common sense.
Everything you've described so far suggests to me that these are models that would have inside them a world model, if you like, to understand the world around them in a bid to make better predictions and better understanding what's going on. And this is something you hear about a lot, which is that for AI models to become truly useful in the 3D physical world, they need to understand the world. They need to understand the basics of what's going on around them, which language models definitely don't do enough anyway. Do you need to also then attach these models to sensory inputs then? For example, you've talked about video, but what about touch and sound and all these other things that humans are very used to doing?
Right. So it's more general than just dealing with the physical world. It's dealing with every situation you encounter, some of which may be virtual worlds or maybe interacting with the internet or a computer system.
Databases, basically.
Or a database, or producing code. So when we program, we have a mental model of what goes on when we execute an instruction. I give you a big array of numbers, and then I call it a sort function. I know that this array of numbers is going to be sorted after I call the sort function. I don't need to know how it works. But I have this mental abstract model of unsorted array calling a sort function. Now it's sorted. And we have this mental model for every instruction that we write in a program. Now, this is not the way current code generation systems work. They basically work by regurgitating code that they've been trained on and sort of adapting it to the current situation, changing the variable names, etc. So they can write code for, relatively sort of stereotypical situations, saving you time, kind of flipping through pages of documentation.
Like a fancy search, basically.
Basically. I mean, think of it as an efficient interface to knowledge. And the AI agent has a lot of stored knowledge, but basically it's learned that by rote. It's not being particularly smart about how to use that knowledge, right? So that requires kind of human leadership, essentially.
Can you give me a vision then? If JEPA is made to work, or something similar in a different architecture is made to work and does the things that you want JEPA to do, what are the sort of the models that we would get as a result for consumers or other people using them? What would they be able to do? How would they be different to the current LLM architectures?
So there are things that will be sort of kind of like LLMs, but they will just work better and possibly answer questions for which they've not been explicitly trained to produce answers.
Because they've got some world models inside.
Because they'll have some world model and, ability to reason, possibly intuitive model of mathematics and geometry and things like that. So that's one thing. And to consumers outside, it will look just like, progressive.
They may not notice.
Continuous progress, a minute progress. But there is one qualitative thing that will occur, which is that with those world models, understanding the physical world, it enables robots to basically learn from the real world, understanding the real world, and learn new tasks extremely quickly, like humans. How is it that we have systems that can pass the bar exam and, compute integrals and solve math problems, but we still don't have a domestic robot that can clear up the dinner table and fill up the dishwasher, a task that any 10-year-old can do the first time they try? We still don't have level 5 self-driving cars, a task that any 17-year-old can learn in about 10 hours of practice.
This is where the new architectures would really make a big difference.
Yes.
Yeah.
So the four things that those new architectures will enable is understanding the physical world, having persistent memory, which is a slightly different thing, being able to reason and plan, and basically solve new problems without being trained to solve them, but just, you look at the situation and you're capable of coming up with a solution or an action to
What sort of
fulfill
timescale
it.
are we talking about?
We're expecting good, perhaps practical results out of those new ideas within the next 3 to 5 years. And it might cause kind of a new revolution in AI, which will make things like humanoid robots practical. Because right now, there's a lot of companies that are building humanoid robots, but no one has the AI techniques to make them smart enough to be useful. Okay, so those people are kind of counting on AI intelligence basically to make sufficient progress for those systems.
I guess it's a hard question to predict because no one could have predicted 10 years ago that we'd be in the situation we're in now with language models. Or maybe some people would have done.
I don't know, some of us would have.
They've gone very fast. So maybe the predictions are difficult to do.
The techniques were known. There had been sort of clear path towards that. And there's been a lot of LLMs produced and even released that just didn't capture the attention of the public like ChatGPT did.
Yeah.
That was a surprise. The fact that ChatGPT captured the interest of the public, that was a surprise, including to OpenAI.
Yeah, I suppose it's the interface, wasn't it? You're sharing a very big prize in engineering this week, the Queen Elizabeth Prize in Engineering, with many of the scientists who have been responsible for the real advancements in machine learning. Your colleagues and friends, Yoshua Bengio, Jeff Hinton, Fei-Fei Li, and others.
John Hopfield.
Yes, John Hopfield, of course.
Jensen Wong.
Yes.
Yes.
And I'm curious to know something. You all have slightly different thoughts about how good or bad AI is going to be for the future. And I enjoy watching you argue about this in public. Jeff Hinton famously thinks that there are negative things in the future. I think Yoshua Bengio is sort of positive and negative. And I wonder where you are in this. You're quite positive, I guess, about the possibilities of language models and AI. How do you sort of reconcile your views with those of your colleagues and friends?
Okay, yeah, we're old friends. We'll have
you can have some pleasant debates about this.
We all have good intentions, but we do disagree on this. I think I'm actually in the majority of opinions.
So just to be clear, what's your sort of prediction?
So my prediction is the potential and actual benefits of AI far outweigh the risks. And there are risks with any new powerful technology. There's no question about this. I disagree with Yoshua and Jeff for different reasons, but Yoshua is worried about bad people doing bad things with AI. And he has been advocating for AI to be kind of somewhat controlled and under lock and key a little bit. And I think that's actually dangerous. So I'm on the side of the fact that AI is going to basically constitute a repository of all human knowledge, and that has to be open source. And yes, there are risks and danger that come with this, but compared to the benefits in progress of science and medicine and access to knowledge, across the world and preservation of cultures and languages, I think the risks and benefits are minimal. Obviously, we have to minimize them, but I'm more confident than Yoshua, I think, about the ability of current institutions to actually do the right thing. Jeff has a different opinion, which is that he believes, first of all, that AI systems, as they exist currently, have subjective experience. I think that's absolutely false. And he also believes that eventually, when they become smarter than us, there will be an inevitable competition between them and us. And
there could be problems.
That's kind of the Terminator scenario or something like this, a common theme in science fiction. I just do not believe that's true, because intelligence is not linked with a desire to dominate. And AI systems will do our bidding. They will be designed to do our bidding. We'll give them goals, and they will accomplish those goals, maybe better than we could, but they will not set their own goals. And the relation that we will have with those systems is that they will be like a staff of virtual people working for us. We'll be their boss. Everybody will be a boss, basically.
Even if they are cleverer than us.
Even if they're clever. Well, it's very common for bosses to not be nearly as smart as their staff, right? It's certainly true for politicians. But it's true for even scientists like me. I like working with people who are smarter than me. It empowers everyone. So it's going to amplify human intelligence.
Yeah, and that's a great place to stop. Thank you so much for your time. I really appreciate it.
Thank you so much.
And thank you for listening. To hear more on the reaction to DeepSeek's new AI model, I really recommend you listen to last week's Money Talks podcast, where Alex Hearn, our AI writer, explains what all the fuss is about. Babbage is produced by Jason Hoskin with mixing and sound design by Nico Rofast. The executive producer is Hannah Mourinho. I'm Alok Jha, and in London, this is The Economist.